This is a live Kubernetes cluster running 11 microservices on AWS EKS. Right now it has 2 nodes. Fixed. No matter how much traffic hits it, it stays at 2 nodes until something changes. This video adds that something. HorizontalPodAutoscaler scaling pods automatically. Karpenter launching new nodes on demand. And a load test that proves both actually work. 2 nodes becomes 8 nodes, automatically, because real load asked for it. Same cluster from V1. Same 11 services, same Helm release, same VPC. Nothing here gets rebuilt, nothing gets migrated. 3 things added on top. First, pod-level autoscaling. Every one of 10 services gets a horizontal pod autoscaler watching CPU and memory. Front-end scaling 3 to 10 replicas. The rest scaling 2 to 6 or 2 to 8 depending on how much traffic each one actually absorbs. Second, node-level autoscaling. Karpenter replaces the fixed-size node group entirely. Instead of 2 nodes sitting there whether they're needed or not, Karpenter watches for pods stuck in pending, launches exactly the T3 small instance needed to fit them, and terminates it again once it's sat idle for a minute. Third, observability. Prometheus scrapes metrics from every pod and from the nodes themselves. Grafana turns that into a dashboard so the scaling decisions are visible while they happen, not just inferred from a kubectl output scrolling past. And underneath all 3 of those, the thing that actually proves they work, a K6 load test, running as a pod inside this same cluster, ramping virtual users against the front-end service until CPU crosses the threshold and both autoscalers have to react. 4 pieces, 1 cluster, nothing torn down to add them. HorizontalPodAutoscaler watches 2 metrics per service, CPU and memory, both against a target utilization. Frontend's target is 70% CPU, minimum 3 replicas, max 10. The moment average CPU across frontend's pods crosses that line, the HPA controller requests more replicas from the deployment. Not instantly to max, it steps up gradually and rechecks. 10 services have one of these configured. Different minute and max per service, because frontend absorbs more traffic than, say, shipping service. This requires one add-on most people forget, metric server. Without it, HPA can query a target all day and get back unknown. No metric server, no scaling, full stop. HPA creates more pods. Something still has to run them. That's Karpenter's job. It watches for pods stuck in pending because nothing in the cluster has room, and it launches exactly the node needed to fit them. Not a fixed-size node group anymore. A node pool with constraints, instance type, capacity type, resource limits. This cluster's node pool is locked to T3. Small on demand only. Same free-tier restriction the original node group had. And consolidation works the other way too. Once load drops and a node sits underused, Karpenter terminates it. Nodes aren't provisioned once and left running. They exist exactly as long as they're needed. This is the node pool. Line 53, the instance type requirement, T3. Small, 1 value, not a range. That's not an optimization choice. This AWS account rejects anything above free-tier eligible at launch. So the constraint here is identical to the one that caused create failed back on the original managed node group. Same lesson, different autoscaler. Line 66, consolidate after, 1M. That's how quickly Karpenter reclaims an underused node once load drops. And line 28, the EC2 node class's role field, references a node IAM role built in Terraform AWS, im.tf, the Karpenter module, plus an Xpod identity agent add-on the controller needs just to fetch its own AWS credentials in cluster. Miss that add-on and Karpenter's pods sit there logging credential timeouts forever, looking healthy on the surface while doing nothing. 2 nodes at rest. This is the baseline before any load. Run kubectl get node claims. This is Karpenter's own internal record. Every node it has ever launched, what triggered it, what instance type it chose, and its current status. Right now it shows the 2 original nodes from the initial cluster. Everything that appears after this point was launched by Karpenter in response to real demand, not pre-provisioned, not guessed. 10 HPAs. All idle right now, CPU and memory both well under target, all sitting at minimum replicas. This is the baseline. Everything from here changes once the load test starts. K6 script, ramping virtual users over 6 stages. Browse, add to cart, checkout, repeat, on a loop, per virtual user. Written at full production scale. A ramp toward 100,000 users, because that's the number worth putting in a README and in this video's title card. Reality check, on camera, no edit. 100,000 virtual users need memory this specific cluster's T3. Small nodes don't have. Each VU carries real overhead, and no amount of horizontal pod scaling changes what a single K6 process can hold in one pod. So the live run you're about to see is scaled to 3,000 VUs. Same ramp shape, same script, numbers sized to what this infrastructure can actually sustain today. That distinction matters more than the number itself. Running the load test inside the cluster as a Kubernetes pod, not from a laptop. If you run K6 from your local machine, your home network becomes the bottleneck, not the application. Running it in cluster means traffic originates from inside the same VPC, same network path a real user request would take through the load balancer. Apply the pod manifest, then follow the logs. Watch the VU count climb. Each stage holds for 2 minutes before ramping to the next level. Front end, 3 replicas to start. Watch the CPU column. Once it crosses 70%, replicas climb. This is live, not scripted. More pods need somewhere to run. Karpenter's watching the same pending pod signal it always watches. 2 nodes. Now 4. Now 8. This is Prometheus data visualized in real time. 3 panels matter most here. Top left, pod count per service. Front-end climbs fastest because it absorbs all inbound traffic first. Top right, node count. This is Karpenter's work made visible. Each step up is a real EC2 instance launching in AWS. Bottom, HPA CPU utilization against the 70% target line. When that line crosses the threshold, the replica count on the left panel responds within 30 seconds. The entire autoscaling system, end-to-end, in one dashboard. Load test ends, ramp down included in the script itself. Replicas scale back toward minimum as CPU drops below target. Nodes follow a beat later. Karpenter waits for a node to sit empty or underused for a full minute before reclaiming it, so it doesn't thrash on a momentary dip. Scale up fast when there's real demand. Scale down carefully. That asymmetry is deliberate, not a bug. HorizontalPodAutoscaler on real CPU and memory metrics. Karpenter provisioning nodes on demand instead of a fixed size group. A load test that actually drives both of them, not just YAML sitting in a repo unverified. And a dashboard proving it, end to end, not a claim in a README. Full repos linked below, same one as last time, new tag. Next, we add full observability. Centralized logging with Loki, distributed tracing with Tempo, and alert rules that fire before users notice something is wrong.